Hello, everyone. Welcome back to CPE 517-WS, Digital and Computer System Architecture. This is part 3 of lecture 10. We talk about consistency and coherence. Okay, so the challenges of parallel processing are from two folds, software and hardware, right? So first, we have to design new algorithms. For instance, if we have an algorithm that performs every step in a serial version, then it will be really bad, right? So how could we take advantage of multi-core? It cannot be like that because every step has to be finished in order to start next step. Second problem is about the hardware, right? The hardware is both from the programmer and the architecture. For example, the NUMA architecture, right? So whenever we access data from the remote memory access, they're going to introduce a lot of latency. Okay. Then how do we deal with it? We can either use the hardware, right? So using hardware to cache some data so that when you access the remote data, it's local. But that will introduce some consistency and coherence issues. Or we can basically solve that problem by restructure the data. So the layout is like, whenever you're accessing some data in this thread, it's always local. So both of them are very active research areas. And both of them, I have a lot of experience how to do that. But today we are talking about computer architecture. So many focus upon hardware. So how hardware helps improve the latency. So that's what I mentioned before. So from multiple boards on a shared bus to multiple processing inside a single chip, we have access for both private data and shared data. So for private data, it's local, it's for sure, right? Because private, nobody's gonna access it. You're gonna be the only one to own it. So we put on this local memory, there's no problem. For shared data, we have to, if we cache it, let's see. It's basically not belonging to anyone, exclusively not belonging to anyone. Both of them can have it. So then how do we deal with it? As what we mentioned before, we can cache the shared data locally. So the problem is, why do we cache the shared data? The problem is that if you didn't cache it, we're going to show you later. Oh, actually, we already showed you in the prior part, right? Part 2. If you didn't cache it, then the very frequent access from this part to remote destination gonna take a lot of time, right? So why don't we do batched access? So batch all the access to that specific process and move it to the local data. So whenever we access it, we access locally, right? So that's easier. That's the reason why we have block device, right? So when we access a file system, we know it's slow, but we have to load all those data from the block device like SSD or HDD from the secondary storage to memory. So then we can do fine-grained access. The same here. When it goes to process, we want to move the data to locally so that we can access all the later on fine-grained access can be local. Okay, so we want to reduce the latency to share data, memory bandwidth, usage for share data, and the interconnect bandwidth, right? So basically, this is the reason that we want to cache the data. We reduce the latency, we save the memory bandwidth, and then we reduce the interconnect bandwidth utilization, right? So these are 3 benefits. And then once you have cached the data locally, you immediately introduce coherence and consistency issues. Let's use 5 minutes to take a look at this motivating question, cache coherence problem. So how it works is like this. Assuming U is stored in memory, and then our target is to first access U equals to 5 in process 1 from the cache. right? And then at the second step, process 3 access U again, okay? And then step 3, process 3 update U from 5 to 7. Then at step 4 and 5, process 1 and process 2 want to access U again. So our question is, will processor 1 and processor 2 see different values after we update U from 5 to 7? So basically, will processor 1 and processor 5 see U equals to 5 or U equals to 7 or other values? Okay, can you guys think about it? Use 5 minutes to think about it and see how we're going to deal with this kind of problem. Okay, so come back to this motivational problem. We say that if we don't ensure the coherence protocol, then it's likely that process 1 and process 2 are going to see different values from U equals to 7. This is why we say that in graphics processing unit, which is cache incoherent device. Well, in order to say consistent or coherent value, what we see here is whenever we update the value at process 3, and then if process 1 and process 2 want to see the value, they should always see the value as like a single threaded update, right? No matter it's right back or right through, if it is right back, that is triggered after the synchronization between the process 3's cache to the memory is done, or even passed from U equals to 7 to U from process 3 directly to process 1 is done after event 4 is triggered, okay? Well, in read through, what we're gonna do is when we update U equals to 7 at event 3, we will also simultaneously update the value in the memory. So that's read through and read back, okay? So this is how it works, and you don't want the programmers to take care of it. That's why GPU programming is relatively harder, because the programmers have to really take care of this kind of coherence issues explicitly by themselves. The intuitive memory model is like, we read an address should return the last value written to that address, no matter who is written to that, right? It's easy in uniprocessor, but it's hard to multiprocessor. There are two problems people being confused about. We're gonna bring this up front and also try to clarify you guys. First is coherence. Coherence concerns about the value of the same location. That is, it's more like a temporal problem, right? So from to the same location, different time, okay? Writes to a particular location will be seen in order. Consistency determines writes to different locations will be seen in order. That makes sense, okay? This is very important. So coherence is like a single value have two copies. They have to temporally consistent. Well, coherence is to the same location but different time. They have to be seen in order. Right? This is our two subtle differences. Okay. So when we talk about preserving the cache coherence, it means we preserve the program order, right? It's the same as what we talked about here. It's the same location, different orders, right? So we preserve the program order. A read by processor P to location X that follows a write by P to X, with no writes to X by another processor occurring between a write and a read. This read always return the value written by P, right? It's related to the same processor. When it comes to two processors, the problem becomes a little bit more complicated. Let's say read by a processor to location X that follows a write by another processor to X returns the value, written value, if the read and the write are sufficiently separated in time and no other writes to X occur between the two accesses. Okay. So essentially, it means the write to X by one processor, and then, sorry, the read by one processor to X. Afterwards, the write to X by another processor should be same in order, right? So if you do the read before that write, you should see the read the old value. If you read or access the value after the write, you should see the updated, the written value. Okay. Write serialization. Writes to the same location, but any two processors should be same in order by all the processors, right? If the value is one and then two are written to a location, processors can never read the value of the two, then later read one. So this is the order, right? So if it's one first, then the value of one updated first. Okay. So the basic schemes to enforce coherence are: we program on multiprocessors, we normally have copies of the same data in several caches, right? Rather than trying to avoid sharing software, SMP uses a hardware protocol to maintain the coherence caches. Okay. It can be either migration or replication. Okay. Migration, data can be moved to a local cache when it's used over there in a transparent fashion. This reduces the latency to access shared data that is located remotely and bandwidth demanded which is demanded on the shared memory. Replication is like for shared data being simultaneously read, since caches make copy of data in local cache. This reduces both the latency of access and contention for read the same data. There are two ways to maintain the coherence in the replication-based case. So typically, migration is possible, but it's in NUMA architecture. But when it goes to cache, it's more replication. So memory has the one copy, cache has another copy. Okay. So how do we maintain the coherence in the replication-based case? There are two ways. First is directory-based. Second is snooping-based. Like it's very much self-explained by the name, right? So directory-based sharing the status of a block of a physical memory kept in one location. Like whoever wants to access this, we have a directory. If you access this, you're gonna be tracked. Okay, snooping is you don't have to track that specific location, but whenever you do anything, you always have to send a signal, like a common data bus you used in 2 lectures ago, right? So it's like a broadcasting. Or the cache controls the controllers monitor or snoop on medium to determine whether they have a copy of the block that is requested on the bus or switch access. Okay. So the coherence protocol has like typically 3 popular copies of them. First is MSI, it's modified, shared, invalidated. So modified means it's dirty, it's updated. Shared means it's empty. Sorry, it's up to date, and it's not updated by anyone. Invalid means this value is not valid. You cannot use it. Messy means exclusive. A cache block is residing only a single cache and is clean. Mosaic means the cache block is owned by current processor and it's out of date in memory. So can you guys use 5 minutes to say why, comparing to MSI, we introduce messy and mosaic? Like why we introduce exclusive and owned? Pause this video by 5 minutes and come back again. Okay, so for exclusive, there's no need to invalidate until a read miss is snooped. Right? It's like this specific cache block is exclusive. That means all the other ones are invalid. Okay. And then owned means the associated cache block is owned by current processor and outdate in memory, it avoids write back when transmitting from modified to shared. So, so that means when you transfer from modified to shared, you still own it because nobody else has this value, right? So that's very important in snooping. If some people is accessing this, then you are only, you can pass this value from this cache to another cache. For messy is also, you can exclusively own this, and other guys who has the value does not have to be invalidated. Okay. This is pretty much for part 3.